Hello, everyone, and welcome to week 8 of climatology. We are starting to synthesize. We're putting all this together. We're starting to kind of put all of our information about data and all the science and the theory and now we understand a bit about the models. Now we get to come back to a topic that I think we're all super familiar with, being that we're all in training for to be environmental scientists. Let's bring a new lens to this, shall we? We've all learned a ton about climate impacts, and we've all thought a ton about climate impacts. But now we've got a bit more background and sort of the data and the models and the theory and the science behind it all. And so hopefully this will be a nice new lens to view it on. So, but first, fun fact for the day, or at least a super incredibly interesting fact for the day, is a series of papers that have come out recently. This one in 2018, you see the citations there. Was It was in Science, right? So the top journal, kind of saying, hey, oh my gosh, if we actually build out the solar and wind potential of just the Sahara Desert, um, we can not only produce enough energy for the world, but we actually might even change the climate enough so that rain and vegetation increase in the Sahara. And they came up with these models based on the GCMs we were talking about last week, as to where these would be and sort of the disruption that it might cause to the regional climate. And they pretty much focused on Sahara. You can kind of see that. They did look over into South America because obviously that's kind of the conveyance right there, or main conveyance. But they kind of looked mostly at Africa and looked at what the potential of this solar and wind farm build out might look like, given in terms of temperature and precipitation. So they definitely showed, sort of a bit of an increase in temperature, certainly by both, but with it came this increase in precipitation, they thought. Well, fast forward to now, a paper just recently came out, from this group, saying, yeah, all good, except it's not just regional. This would be a global redistribution of temperature and precipitation. They came up with this kind of figure, which is awfully busy. But all this is to say, if it does increase precipitation in the Sahara, that means it takes it out of somewhere else. And their conclusion was it's largely going to cause, just major droughts up. Oh, I think in Europe, and well, I mean, it looks like you're losing some significant precipitation, kind of here, off of South America. Um, but basically said, yeah, this would actually have a pretty significant impact, globally. Not only would it increase global temperature by potentially like a half a degree. So this is just the fact that, and they're primarily looking at solar in this follow-up paper, um, but but just the fact that solar panels are primarily black, right? Because that helps them absorb more of the solar radiation coming in. Well, but then they act like a black body, and even though all the panel is there to convert that solar energy into electricity, for us, it's only about 15, maybe 20% effective, or efficient at converting that energy. And so the rest of it gets lost as, you guessed it, heat, emitted radiation, heat. And so, just the expanse that, and this is all hypothetical, right? But the expanse of covering a quarter of the Sahara with solar panels would generate enough heat to raise the global temperature a half degree to a whole degree Fahrenheit, just from the presence of those things. So fascinating, right? We're talking about impacts. We're talking about models last week. This is a really cool application and very interesting outcomes and considerations. Well, this is why we have to look a bit more at scenarios, because as the former director of defense for the U.S. said, the known unknowns are totally fine. We can handle those, but the unknown unknowns, and this would qualify as an unknown unknown. Um, we know that there's unknowns around climate. That's fine, but would we necessarily, without papers like this, understand the potential impact of solar panels on climate? I mean, we anticipate the positive impact, but not necessarily all the negative impacts. And so this was I thought this was a really interesting kind of take on a pretty contemporary issue. Which brings us into talking about the chapter and talking about the impacts of all these climate models and what we anticipate, basically, right, based on our current understanding of climate and climatology and climate change. And I thought it was really important to kind of just do this first rundown of projections versus predictions, because this is something that well, it's challenged us as scientists. The scientific community has really challenged us because we've used these words in different ways than perhaps society expects us to use these words. And so this guy, Mike McCracken, he was with the U.S. Global Change Research Program. I think he's at NCAR there in Boulder, Colorado still, but he had laid this out really nicely. And this is really key to set the stage for thinking about impacts. A prediction is largely a probabilistic statement, meaning it's solely based on statistics. And you remember that climatology is primarily a statistical kind of science. Um, but but probability, right? Probabilistic statistics is not just regular statistics. It's not descriptive statistics, where we're talking about mean, median, modes, and all those kinds of things, right? Or even extremes. Probabilistic means that we have enough data and enough horsepower to calculate probabilities of something occurring, which we do often in climatology. But that does not mean that any of our climatological models are predictive. It's something, so a prediction is a probabilistic statement of something that, or that something will happen in the future based on what's known today. And what's known today is the really important part. So it assumes related conditions will not change, i.e., the relationship between temperature and carbon concentrations won't change. Right? That would be one condition. Another condition would be we don't change the relative distribution of precipitation or water vapor in the Earth's atmosphere. Those kind of conditions don't change in these probabilistic predictions, which means that the initial condition at which point you start the model forward, right, is really 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 important, because that's where the prediction is based off of, is that initial condition. And so you can kind of think of forecasts, like weather forecasts, as being in the prediction camp. It is, right, and it's largely considered the best of the predictions, or some composite of the predictions, like the mean model kind of thing. But those are limited. A projection is what we largely deal with in climatology, and a projection is still a probabilistic statement that's plausible, and he uses the word possible, that something will happen in the future if, and that's really important, if certain conditions develop. So this means that your boundary conditions can kind of be varied. And this is why we have these things called scenarios. Scenarios are simply just different assumptions about how the future will change or how the future will develop. This is really, really, really important, because it gets away from this limitation of initial condition and assuming conditions won't change. It says, no, we get it. Maybe our science is imperfect right now. Let's build in a little bit of flexibility. What if we're wrong about cloud formations here? What if we're wrong about aerosols there? What if we're wrong about the amount of carbon that human society will produce? This is the differences between a projection and a prediction. Projections allow you to explore a little bit more. Predictions are purely probabilistic. They're They're predictions, right? To most decision makers, they want a prediction, right? They want to know what is likely to happen. Projection is like 4 predictions, sort of, or 6 or 8 or 10, right? And decision makers largely don't like that. They don't like you to say, well, the science is imperfect in these key ways. Let's explore that uncertainty with a couple of different changes and assumptions. And so that means the best projection is, you know, first has to consider the results of the state of the art science models. But it's also largely why we do those mean models, because we're kind of covering the range of uncertainty with these scenarios. And we're going to dig into those just a little bit more. Um, so the idea is that when you average that out, then you have something more representative of the future. It's not perfect. It's not going to be a prediction, even when you model out all those projections and average them out. It's still not a prediction, because a prediction really holds those conditions constant. And that's really, 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 really important to understand. So the book kind of introduced you several times, and I have to these older scenarios. I'm calling them older because they were developed in 2007. So the SRES. Um, the book mentions these. These are from the AR4 IPCC report. So the IPCC report that came out in 2007 was the annual report 4. And it was like, as I mentioned before, it was the first attempt at defining these scenarios that described different assumptions, not only within the models, but about how people and society in the world would change, both in terms of human culture, but also ecological changes and vegetation and that sort of thing. And so these are the suite of scenarios that the IPCC came up with. And A is if the first letter is A, that means that it's largely a anthropogenic kind of driven future, I guess, anthropogenic carbon driven future. And B means that it's a bit more baseline or biological or biome or whatever you kind of want to think, but it's the less extreme kind of scenarios. And so you can kind of see how it lays out here. This is the temperature change relative to the different scenarios. And that right off the bat gives you just a sense of like, okay, B1 was like the really low scenario. A1T was sort of a very reasonable one. B2 still pretty low and in line with this one. And you kind of increase. And then you get to the A1F1, which is what you guys played with in the Earth 1, Earth 2 models, when it was projecting 1,000 parts per million carbon. That was the A1F1. That was largely considered the most extreme scenario anyone could possibly imagine back in 2005-6 when they were writing this, and they gave you a little bit of probability around those things. And then the associated sea level rise. You can find this all in the IPCC archive, which is pretty cool. You can read more about it, and it's really interesting because each of these scenarios go into all kinds of the assumptions, like I said, about both human and natural ecosystems. And so, like, for example, the A1T, the T stands for technological. So A1 means that it's an anthropogenic, but carbon future. But we develop enough technology actually to mitigate much of the carbon. So A1, the first scenario of the anthropogenic, assumes sort of the trajectory that we're going on back in the early 2000s for carbon emissions, but we would come up with enough technological solutions to capture most of that carbon. So it doesn't actually reduce the carbon emission very much, and more captures it, versus the A1B, still the same trajectory, but we start to tail it off towards the end of the century. We don't continue at exponential, which is what the A1F1 kind of just takes our trend of carbon emissions and shoots it out with absolutely no mitigation whatsoever. And that's the extreme, right? So do nothing, and we continue to really increase. Well, here's the actual written out scenario. So if you're interested, yeah, it's really pretty awesome. The little scenario snippets, and if you want to know more about these scenarios and the use in science, like I said before, this is something that I do a lot of. I've written I think about 50 or 60 scenarios in my life now, for different contexts. And it's just this really nice way of integrating social ecological kind of information into a framework that allows you to model it, which is really cool. Um, so this all relates to the more recent scenarios. Now they got rid of the word scenario because, well, lots of reasons, sadly. But they got rid of it in the name, but it's still very much, sort of um, the the terminology we use for describing these variants of the future. But instead of calling them the sort of SRES, we're now calling them RCPs, representative concentration pathways, because it's a bit more explicit in what it's saying. Basically, we're varying the amount of CO2 concentrations. And it's more than just CO2, as you can see from this figure. We're looking at methane and nitrous and sulfur oxide kind of, or dioxide kind of concentrations. So, but it's the concentrations of these aerosols and greenhouse gases that we're modeling. So we're coming up with representative concentrations of these, greenhouse gases and aerosols. And then we kind of describe how sociologically we get there. So these are not just numbers grabbed out of thin air, nor are they simple linear regressions of, oh, well, there's going to be 8 billion and then 9 billion and then 10 billion people on the world, and each person generates this much, carbon. They're pretty sophisticated. They're pretty well defined, to be honest, pretty well modeled. But you can kind of see we're still doing the same thing in terms of covering a broad range of future concentrations of CO2, methane, nitrous, and sulfur dioxides, which is really good, right? And it kind of gives the colors over here. But it's really kind of key, I would say, to kind of just almost memorize these, right? Just remember that 2.2, it goes into, well, I'm going to show you in a second, just the relative forcing of carbon. So 2.2, 4.5, 6, and 8.5 really represent to the effect that humans are going to influence the global climate in the future. And the higher the number, the more influence we have in terms of our carbon forcing. So they kind of talk about the relative parts per million, right? Remembering that right now we're sitting right at the doorstep of 430, we're like 425, right? So we're very, very close already to the RCP 2.6. Actually, RCP 2.6, might soon actually not be realistic, which is very much a discussion point in the literature right now. And then here we get down to sort of the radiative forcings, but I kind of wanted to go back to the figure that the book provided, which does this really nice comparison between anthropogenic radiative forcing of the different RCPs and the SRESs. And I like that he included the old scenarios compared to sort of the new RCPs, because it shows that, yeah, generally we haven't actually changed the nature of those slopes. That's not great news, but really it means that we haven't actually come up with a new way to sort of think about this high emission future. We have written off some other plausible scenarios. This A1B is no longer captured, and you'll see too that this 2.6, RCP 2.6, was simply not at all considered in the old scenarios, which is really important because while a lot of folks say that this RCP 2.6 is not feasible anymore, it provides the baseline of what could happen if we were really smart and if we were really proactive in our management of not only carbon but all those aerosols. We could conceptually, theoretically, in a modeling framework, we could we could actually keep this radiative forcing down, this anthropogenic radiative forcing down. And this kind of shows what it would look like, I think, without the anthropogenic. Book didn't do a great job explaining this, but that's the best I can kind of come up with. So that's the human footprint, or the human anthropogenic contributions removed, and the various model runs. But yeah, so this is really the key, right? So we've got sort of our high emission scenarios, we've got our 2 medium, and then we've got the idealized state for maintaining the current climate as the RCP 2.6. But there's some uncertainty around these, right? Remember that each of these scenarios are being run by each of the models, and each model has different assumptions about exactly how these different levels of greenhouse gases and aerosols are going to interact and play out in the climate, and both in the the atmosphere and the air temperature, but also the ocean and the ocean temperature. So here's a nice comparison of sort of the uncertainty associated with each of the RCPs. So again, 2.6 is the super low, 4 or 5, and 4.5 and 6 are the moderates, and 8.5 is the extreme. You see this CMIP 5 versus IAM. So the CMIP is the comparative model comparative model inter comparison project. I don't know what that first C stands for, but basically this is the this is looking across all the data sets for global temperature, and using that as the sole output from a global circulation model. This is different from the IAM, which is the integrated assessment models. And the integrated assessment models are the ones that take into account vegetation and humans as sort of this dynamic feedback. So it's a little smoother, I think. Yeah, it's a little smoother, and I think that's largely because you kind of have these buffering effects. Book didn't really talk about this, and I'm really just kind of hypothesizing on that. But I'm assuming that the smoother nature of those that IAM lines just represents just the sort of the buffering effects, whereas the high variability of the CMIP, I mean, that's really trying to match interannual observations. So it's going to be a lot more kind of ups and downs, where the IAM is going to capture the general trends. But nonetheless, I mean, the two match pretty nicely, right? The biggest departure comes in that RCP 8.5, and this is really key. So right, we've got the uncertainty associated with all the models based on the actual observations, right? So the black line here is actual observations, and then so everything gray and black, it's actual observations. IAM is still obviously modeled, and then you get the different RCP scenarios. But this uncertainty around the extreme is really, really important. It's better captured here in this graphic, right? That kind of talks about, okay, like, yeah, there's a lot of uncertainty in that bigger one because, well, we don't really have any record of those levels of carbon. I mean, we've extrapolated backwards for sure, but there's no record of these levels of carbon dioxide in the atmosphere, for at least a million years, right? And probably like 3 or 4 million years. Remember, we've got ice age or ice core records back 800,000 years, and we haven't seen this kind of carbon dioxide. And so, plate tectonics, all these things have changed in the last million or 2 or 3 years, which kind of makes it really hard to anticipate what exactly those super high carbon futures are going to look like. And so it gets really fuzzy, and especially the further you go out in time, right? So where we've got reasonable amounts of carbon dioxide via the RCPs and other greenhouse gases, we've got tighter kind of bounds because we just sort of understand the physics a little better, especially if we just go out to 2100. I mean, by the end of the century, we're still like the uncertainty is increasing. But out to 2150, I mean, look, there is really strong agreement across all the models, we've got really strong agreement out to like 2050. So for the next 20, 30, 40 years, we can have really high confidence that all the models are sort of saying the same thing. And even across the scenarios, we've got some strong similarities, right? Like so the 2.6, I mean, it assumes like significant carbon policies, super significant carbon policies. Like we can only emit another 500 gigatons, right, of carbon. That's it, for it to level off, and it just recognizes, right, that we've got some inertia right now with the amount of carbon we've already put into the atmosphere. So it takes until about 2040. I think you've even seen 2045 till that tails off and then starts the gradual decline down. Um, but everything for the next 20 years is I mean, all the models agree. And so remember, this is the number of models that have done each scenario. So not every modeling group does all RCPs or all scenarios in the former assessment. um, but but most of them do a lot of the scenarios, a lot of the RCPs, at least to 2100. After 2100, I mean, it's ridiculous supercomputing, and yeah, a lot of groups just won't go that far out. Even though it's really crucial for things like ecological responses, where ecosystems move on that century timescale. um, it's yeah, a lot of groups just do not feel comfortable modeling that far out. And so it's just really important to kind of remember that yeah, the higher emission scenario, there's a lot more uncertainty associated with it. And with the less ones, it's there's less uncertainty. There's still serious uncertainty associated with all of them, especially by the end of the century, this century. Um, but really, this take home of like next 20, 30 years, and as we continue to refine our models, right, and as we continue to collect more data and build more sophisticated computers that can run these models, our predictions are projections. See, it's really careful. You got to be careful. Our projections are going to get better and even closer, and less uncertainty associated with it, as we move forward in time. And so there's a lot of confidence in sort of thinking in the near term about these model outputs. Even though there's uncertainty associated with it, we can have a lot of confidence over the next 20 to 30 years. And this is I liked this graph too, because it really, and he didn't cover this until the end of this little section, but I think it's really important to kind of realize that like these RCPs really do mark a departure from what we've seen in the past. Um, and that's really, really, really important, because it means that we are in this theoretical modeling realm, right? If we don't have observations to suggest, what would happen in the world, with certain CO2 emissions in this case, then we have to move outside of that, because we know we're on this trajectory. We know that we have the potential. We know how much carbon is locked up in reserves, and we know that if we continue to liberate it at the rates that we are going at, that we are departing from the norm. And so the gray here represents the norm in terms of relationship between carbon and temperature anomalies. And these scenarios, the RCP range, it covers a lot of the norm for sure, especially if you think of just the RCP 2.6, and 4.5. Still well within the range. And even RCP 6 is still within the range of normal, quote unquote, normal. CO2 to temperature relationship. But the RCP 8.5, again, because we don't have records. We don't know exactly. We have experiments, certainly, but we don't have records of this. We are going outside of the normal variability. And that's really, really, really key. Okay, so with all that, now let's look at some things that you've already looked at, I'm sure, in so many environmental science classes, and probably throughout your life now. We've seen maps like this, where we just see these super, super Well, red maps, right? Where we're just saying, oh, it's just all going to warm. It's just going to be crazy, and some places are going to warm more than others. But it is important to kind of remember. I mean, that's the goal of these models, is to kind of understand what could be the future. So this shows the outputs of these models. We gain a lot of confidence because this still matches our conceptual understanding of how the climate works. We see the polar amplification, right? We see oceans, um, having less of a less of effect than terrestrial, because that land ocean dichotomy, right? That's all really important, and it matches very much what we've seen, at least since the latest glacial maxima. So we've got, several 100,000 years of good evidence that yes, this is how climate plays out. And this is, not going back 700,000 years. This is just going out 80 to 90 years from when this was run. Um, and right, remember, the Arctic is warming twice the rate. I mean, hopefully I've hit that enough that you guys really get that, because remember, that polar amplification is so huge. The fact that we have so much more land mass up in the northern hemisphere near the North Pole compared to like the South Pole, it means that we don't have enough ocean to buffer all this warming. And we already have the conveyor belt kind of moving heat up there is just as fast as it can, and as long as it stays relatively cool, it's going to just keep absorbing more and more and more and more and more of that heat. So the relative change is significant, even though the absolute values are, it's not like it's going to be 80 and the North Slope of Alaska, although it might be. It's more that change over the baseline right now, and that's really important too. So this scale, right, shows we're going to have decreases compared to the mean, compared to the and typically when you see these global maps, it's that 1880 or 1850 to 2000 mean. And so this is all that departure. So it's not, I mean, it could sort of be read like the temperature anomalies, but it's the departure from the norm. So on average, they expect, up to 11 degrees in Siberia, right? Centigrade under this scenario. And that's important, right? So same thing on the precipitation, although, as you read and as we've kind of discussed, this is really, really, really hard to capture in these models, simply because our understanding of clouds and aerosols are still just incomplete. So there's a lot more variability between models. And these are obviously model means, again, because it's not specifying any given CMIP model. But you can kind of see, right, just the anticipated changes. But I want to take this chance, though, to kind of point something out, right? So you're used to seeing these kind of figures, but how often do you look at this up here? How often do you look to see, well, what assumptions is this panel of maps based off of? Because it's really important that in order to be climate literate folks, that always to check for, okay, what RCP, or previously what SRES, or in the future it's going to be this shared socioeconomic pathways, SSPs, I think. Which one are they talking about here? So in this case, we're showing the extreme, the RCP 8.5, right? The one that has a bit more uncertainty. And especially look at the time frame. It's the 2080 to 2100. So this is definitely the end of the century. We have more uncertainty associated with this, and this is the extreme. It's not to say that we shouldn't be looking at these, but we should definitely just acknowledge, okay, this is on the extreme side, and there's some uncertainty associated with the extreme side. It's good for bracketing our understanding, right? So this is, I don't want to say as bad as it gets, because we just don't really don't understand. It could get much, much worse, right? And as we're going to talk a lot about this week and in the coming weeks, all climate change is not bad necessarily. So this is just an extreme on the high side. And that's really key. So if you think about that, yeah, the dry places are going to get drier. The wet places are going to get wetter. You're going to have more evapotranspiration, largely because of just that increased temperature, right? You get drying it happening, and you get that stronger, Hadley cell developing. And so it's just going to suck even more water vapor out in those subtropics. You are going to have, pretty significant changes in humidity just because it is generally warmer, especially over the landmass. So, relative humidity is definitely anticipated to go down pretty much globally, except for parts of Africa. And therefore, things like runoff and soil moisture are gonna change pretty significantly. So remember, in all these figures, the cross hatching or the dots, that means that there's statistically significant changes, right? So don't just focus on the colors, but focus on the colors and whether or not it has that dot stippling or the hatching, because that denotes the significant areas, right? And so let me see. Yeah. So runoff, soil moisture, definitely going to change, but in really heterogeneous patterns, right? Looking southwest, U.S., it's not great. Runoff's going to go down pretty significantly, which means soil moisture is going to go down pretty significantly. Yeah, those are big patterns to kind of observe. And then certainly on the sea ice kind of side as well. I like this a little bit more because, again, look at the dates towards the end of the century, but at least you have multiple scenarios. You have all four of them, right? You have the low, the 2.6, you have the two moderates, and then you have the extreme. And this just gives you context, right? It's like, okay, best case scenario, if you're interested in preserving sea ice and the climate that we have now, best case scenario, it's going to look like this, and the purple lines kind of denote current, I believe. I want to make sure that I get that right. Yeah, I believe the purple and white or maybe the white is the max and the purple is the current. Anyway, and then so the white shading is so the maximum, and the gray would then be representative of the minimum. And so the minimum, change, in that low scenario looks like this. The maximum looks like this in the 4.5, and the minimum looks like that. It's sort of scary. So just a step up from the best case. We have not very much going on. Here again, maximum, minimum, pretty sad looking. And then RCP 8.5, it's just gone. Right? Unless we develop some new understanding, some feedback that allows that ice to persist, it's going to go away. There's not going to be any more annual ice in the North Pole. That's pretty big, right? It's pretty significant. So this is all based in September, sort of, right? Estimates, right? And then, of course, all this plays into the sea level rise as well. There's lots of discussion around this. It's really important, and hopefully you guys know that, sort of looking at the magnitude of these sea level rise estimates according to the projections. So again, the low projection, it's very reasonable, but there's still an awful lot of inertia towards sea level rise, right? So just given the carbon that we put into the Earth's atmosphere already, best case, we're going to see a 0.4 meter sea level rise by the end of the century. Best case estimated. There's some uncertainty of it. Could be all the way up to like 0.6, right? Versus 8.5, that's when we get all the way up to, by the end of the century, up to a whole meter. So 3.2 feet of sea level rise. That's global sea level rise. And we know that this varies tremendously across the Earth's surface, right? Some places sea level is going down because of the isostatic rebound. When you lose glaciers, it takes pressure off the continental plate. It's going down in some places because of simply just changes in the ocean chemistry, right? Heat expands the water. So in those really cold areas where you get the deeper cold water upwelling, especially like Greenland, as the fresh water discharges and it's so cold, we actually see a bit of a reduction in sea level rise there. Probably isostatic as well, but just because it condenses, right? The cold water kind of condenses, and so you don't get that the rising or the expansion of water up there. Um, but that means then if we're looking at global and it's not going up in some places, the whole meter or at all, that means it's making up for it somewhere else, right? So when we think about a global mean, if somewhere is going down, then somewhere has to be then going up double the amount. And so thinking about 2 meters of sea level rise in some places, and that's really, really significant, 6 feet more of water on top of where the ocean is right now is fairly significant, given that 75% ish of the world's population lives within a couple of kilometers of the ocean. That's kind of huge, right? Um, and more importantly, hopefully you guys have talked about this in other classes. I mean, the sea level rise is certainly going to suck for places like the Netherlands, where most of the country is below sea level. But it's going to be particularly challenging when you start thinking about, well, but seas are not static, and it's the sea surges and this, storm surges that are really, really potentially problematic when you add in sea level rise on top of this. That's certainly what I focused in on in Australia. 1 meter doesn't really impact a whole bunch of communities down in Australia, but you get 1 meter plus an average storm surge of 2 to 3 meters, and all of a sudden you're flooding out half of Brisbane. I mean, that's the difference, right? 1 meter, we've kind of got some resiliency against. 2 to 3, no, no, we really haven't planned for that in our city infrastructure. So, and sea level rise is kind of one of those things that kind of led into this discussion on tipping point, right? So, melting of the Greenland ice sheet. The book kind of talked about these different tipping points, and there's certainly a lot of them out there. Remember, tipping point just means once you've crossed the threshold, you can't go back, right? So once you melt the Greenland ice sheet, you can't go back because ice requires other ice to kind of form and build off of to become these big extent, kind of ice caps, the polar ice caps. So once you melt Greenland ice sheet, there's no recovery. You can have sea ice reform, but you're not going to get the whole ice sheet until everything completely changes, right? All the temperature goes plummeting. Same for the West Antarctic ice sheet. That's a tipping point that you can't go back on. Collapse of the AMOC, right? The Atlantic Meridional Overturning Circulation. This is what we've talked about a couple of times. This is what led to the day after tomorrow, right? And then ecosystems and shifts and species extinction, which I'll give a quick example of here in a sec. So just talking about that Atlantic Meridional or returning circulation, there's some really interesting work coming out, like I've been mentioning for the past few weeks, kind of tying this hypothesis that if you slow that down, remember that's the Gulf Stream, that's the conveyor belt that makes Europe habitable and most of the East Coast, fairly moderate given their latitude. And we're just seeing, this is over the last 1,000 years. We are seeing, yeah, absolutely. There's a bit of a cool down happening in that. And a cool down means that it's slowing down, and it's slowing down largely because of this. This is your cool down. And again, it's because of the melting of Greenland. So it's real warm up there. It's discharging all that fresh, cool, cold water into there, and it's keeping it really, really cool, which is going to slow down, they think, and there's certainly some evidence that it's slowing down the conveyor belt. And that's a tipping point, right? Because if it slows down, if it stops, which nobody's forecasting that at all. Nobody's predicting that even, but they are projecting, some plausible scenarios when this might occur. Nobody is projecting in the next 100 years, which is good. But it's certainly a physical potential. It's certainly theoretically plausible, and there's actually some evidence that it may be happening right now. So yeah, so the book kind of had these nice little examples. I'm going to bring in some more for the next lecture because this one's gone already too long. But thinking about future potential vegetation. So this is, vegetation is mapped by satellite imagery in 1990, and this is what it could change into, by the end of the century. And so it's pretty significant, right? Like in this change, anything that's gray doesn't change. Anything that's colored is a new distribution for that vegetation, new place where it's going to be, where it's going to be suitable at least. And there's uncertainty associated with these as well, right? We have some real strong confidence in sort of the closer areas, closer moving areas, because we already see the evidence. We've seen it actually. We've seen it with aspens. This is the link. If you clicked on the link out of the chapter, this brought us over to the Canadian Forestry Service because they're really key. This is just zooming in and give it a little bit more context. I mean, aspens are a super sensitive species to climate. They reproduce asexually generally. It's one of the largest living organisms. Is just an aspen that's a single individual that occupies hundreds of acres because they all reproduce through their roots. Super sensitive. So you take out one of those mega organisms and you've lost a good bit of their potential distribution. So you see a lot of this kind of work happening using these RCPs, trying to figure out, okay, like, geez, what is this? And remember, we got to focus in. So we typically focus on the worst case because that just provides that bracket. It provides that, okay, this is as bad as it might get. It's not the worst, but this is as bad as it might get. Within the realm of sort of scientific plausibility. Let's use that as a bracket and start to try to mitigate for this. Audubon, oh dear, that didn't reproduce very well at all. Audubon's done this with I think there was 75 species of birds, basically looking at their current distribution and thinking about where they're going to lose, where they're going to gain. I'll just explain it briefly and try to find a better version soon. The red is the loss. So this is where you can find common loon right now. So that would be, it's about 21% of its range lost. 73% of its range is still maintained. That's the oranges and yellows and greens. And then blue represents the expanded range. So they're going to lose 27%, but they're going to gain 18%. And this is just like suitability kind of stuff. So these are the kinds of ways that we're using this, right? So using these RCPs, and that again, this is the 8.5. It doesn't say it in the figure itself, but it's the 8.5 RCP. And the book ended up with kind of talking about fires, right? And just thinking about the projected change in fire probability. And there's just like precipitation, it's even more complicated to predict things like this. There's a huge amount of uncertainty. And this was using the old scenarios. This is the SRES A2, so not the extreme, which is useful to remember again, right? Not the extreme, not the A1F1, which is comparable to our RCP 8.5 now. But you just see these pretty significant kind of changes, increases in fire probability. I mean, a 25% increase in fire probability is pretty enormous, right? If you've got a fire return interval of 100 years and you increase the fire probability by 25%, that means it's a 75% or 75 year return interval. It's significant, right? And I just wanted to highlight, because this is my colleague John, and that's Aboxiglu. That's how you pronounce his last name, Aboxiglu. He and a colleague wrote this paper in 2016 for the Proceedings of National Academy of Sciences. It's like one of the most cited papers now because he laid the foundation for really tying these kinds of models, these fire chain probability kind of models, to anthropogenic forcing carbon or global circulation models. And so if you're interested in this, especially, I know there's some groups dealing with fires, wildfire, and this was specifically in Western US forests. Here's the link to that because I think it's well worth the read. So yeah, that's it for the impact so far. We're gonna get a bit more into the sort of the regional impacts and give you more examples in the next lecture. Um, but hopefully you gained just a slightly new lens to these impacts now that we've kind of gone through a lot of the science and data and models behind them.